This is Jacob's Algebra, Chapter 14, Lesson 5. Okay, so in Lesson 5, we're going to learn about the real number system and the parts of the real number system. So often you'll see it pictured in a series of concentric circles, and each circle has a set of numbers that lives inside of it. And so we might look at it like this. Hold on, let me get all my circles on here. Okay, so in this tiny little circle in here are our counting numbers. Okay, the counting numbers are 1, 2, 3, 4, the regular counting numbers that you would count objects with. Notice that 0 is not a counting number because you don't count 0 of something. If there's nothing there, you can't count it. So the counting numbers start with 1. Then you have the integers. The integers include the counting numbers. So the counting numbers you'll see are inside of them. But the integers are also -10, -5, -2, 0, 10, 100. So the integers are all the positive and negative, well, all the counting numbers and the negatives of all the counting numbers and 0. So that's why you see the counting numbers inside of the integer circle because counting numbers are also integers. And then in the next circle out, you see rational numbers. Now, rational numbers, remember, are any number that you can write as a fraction with an integer in the numerator and the denominator. So this would be like 7/3 and -10 sevenths and 41 halves. Those would be our rational numbers. Over here in this other circle on the right, we have our irrational numbers. Notice the irrational numbers don't overlap the rational numbers at all. The irrational numbers are numbers like square root of 2 and cube root of 10 and pi. Those are all irrational numbers. None of these numbers can be written as a fraction of two integers. And then the big circle that encompasses all of these circles is real numbers. All of these are real numbers. In this book, we are not going to get into imaginary numbers. You learn about imaginary numbers in Algebra 2. But real numbers include the rational numbers and the irrational numbers. Any number that is irrational cannot be rational. A rational number can be an integer. A rational number can be a counting number. All of these are real numbers. Now, we say that a set of numbers is closed on an operation if the result when you perform that operation on members of the set is always inside of the set. So if you think about like counting numbers, is addition closed on counting numbers? Well, yes, because if you add any two counting numbers, you will get another number that is a positive integer. But subtraction is not closed on the counting numbers because you could subtract and say 2 minus 4, and your answer would be -2. -2 is an integer. It's not a counting number. So not all operations are closed on all sets. Okay, now let's look at the first problem here. Number 4 asks about a series of asks you to classify a series of different numbers. So I'm going to pause the recording and get those up on the screen. Okay, so these are all the numbers listed for number 4, and all the questions in number 4 are about these numbers. Now, before I get to these questions, let's try classifying these numbers. 8 is a counting number, so I'm going to call it a CN. 8 is also an integer, so I'm going to call that an INT because I already used capital I for irrational. I don't want to use capital I for to mean integer. 0.8. 0.8 can be written as 8/10. Since it can be written as 8/10, that means that it is a rational number. So I'm just going to write rat. 0.8 continuous. Remember a couple of lessons ago we learned how to take any repeating decimal and write it as a rational number. So this is rational. 0 to the 8th. Well, 0 to the 8th is 0. That is an integer. It's not a counting number because remember, you don't count 0 items. You have to start counting with 1. Square root of 8. That can simplify to 2 square root 2. That is irrational. So I'm going to call that IRR. Now we have cube root of 8. Well, the cube root of 8 is 2 because 2 cubed is 8. And that is a counting number. So I'm going to call that CN. Negative 8. Well, it's not a counting number because it's negative. None of our counting numbers are negative. So this is an integer. So I'm going to write int. 1/8. Well, the definition of a rational number is a fraction of two integers. So that is a rational number. And then we have 8 pi. I know that doesn't look too much like pi. Let me actually try and fix that. Okay. That didn't work real well. Still didn't work real well. Okay. 8 pi. There we go. Okay, pi is irrational. And since we're multiplying by an irrational number, that means we have an irrational number. And then 8 squared. 8 squared is 64. That's a counting number, so I'm going to call that CN. Okay, so question A. Which numbers are counting numbers? Well, 8 is a counting number, obviously. 0 is not a counting number. These numbers that I listed as just rational, those are not counting numbers. 2 is a counting number. I'm sorry, that was actually cube root of 8 is equal to 2, which is a counting number. And then 8 squared is 64, which is a counting number. So 8 squared. Okay, part B asks us which of these are integers but not counting numbers. Well, we can't count 8 because that's already a counting number, so we don't want to count that one. 0 to the 8th is an integer but is not a counting number. Negative 8 is an integer but not a counting number. And that's all we have that is an integer that is not a counting number. If we wanted to include the counting numbers also, then we would include 8, cube root of 8, and 8 squared. Okay, part C wants to know which numbers are rational but not integers. Okay, so the rational numbers are going to be 0.8 right here, 0.8 repeating, 0.8 repeating, and then 1/8. Those are all the rational numbers that are not also integers. And then part D wants to know which numbers are real but not rational. Well, if they're real but not rational, then they must be irrational. And so those would be square root of 8 right here and 8 pi. So for homework, I assigned problem number 11, which is very much like this one. You'll be given a list of numbers, and you have to identify these numbers as counting numbers or as integers but not counting numbers, and rational but not integers, because all integers are rational. So you will be given a set of numbers very similar to this one. And what you need to do for your whole set of numbers is see if the number you're given can be simplified. And if it can, is that simplified number a counting number, an integer, a rational number, or an irrational number? Okay, now let's take a look at problem number 5. Problem number 5 says the counting numbers are closed with respect to addition because the sum of any two counting numbers is also a counting number. Tell whether or not the counting numbers are closed with respect to each of the following examples. So we're going to do this with counting. Sorry, my pen went out of pen mode. We're going to do this with counting numbers. Remember, counting numbers are the positive integers. So the first one it's asking about is subtraction. Is the set of counting numbers closed for subtraction? And the answer to that is no, because you could do 2 minus 4. And 2 minus 4 is negative 2. Negative 2 is not a counting number. Okay, part B asks if multiplication is closed. And that's true. If you take any two counting numbers and multiply them together, multiplying any two positive integers together will give you another positive integer. So that's going to be true. Okay, part C, division. It is not closed with respect to division. If you take 3 and divide it by 5, you're going to get 0.6. That is not a counting number. So it is not closed with respect to division. Part D is asking about cubing. So if you cube a counting number, will you still get a counting number? Well, that's going to be true. If you take any counting number and multiply it by itself, you will get another counting number. And if you multiply it by itself again, you will get another counting number. So that's always going to be true. And then part E says taking the square root. So if you take the square root of any counting number, will you always get a counting number? And that is not true. If you took the square root of 4, yes, you would get a counting number. But if you took the square root of 5, you would get an irrational number. This is why the set of counting numbers is not closed on the operation of taking square roots. So number 5 is very similar to number 12. And in fact, it's also similar to these next couple of questions. Number 6 asks about the set of even integers. So for number 6, we're going to be looking at even integers. So this means -10, -8, -6, 0, 2, 4, 6, going all the way in both directions. Only the even numbers though. And 0 is an even number. Okay. Is addition closed with respect to even integers? Well, let's see. If we take any two even integers and add them together, will we always get an even integer? And the answer to that is actually yes. You add any two even integers together, doesn't matter what they are, you will get another even integer. Part B, what about subtraction? Can we subtract any two even integers and get another even integer? That is also true. Okay, part C, multiplication. If we multiply any two even numbers, will we always get an even number? Yes, we will. Part D, division. If we divide any two even numbers, will we always get an even number? That one is not true, because we could take 10 and divide it by 8. And when we divide 10 by 8, we get 5/4, which is 1.25, and that is not an even number. So division is not closed on even integers. And then question E is cubing. If you cube an even integer, will you always get an even integer? And that one is true, so we'll say yes. So for each question that it asks, you have to see, if I perform that operation on any two numbers in the set, will I always get a number that's still in the set? And you may have to think about trying a couple of different examples to see if you can find one that makes it not true. For even integers, it's going to be true for almost everything. It's not true for division. It's also not true for taking any kind of root. Anytime you take a root, there's a possibility of getting a number that's not an even integer. While the square root of 4 is an even integer, the square root of 6 is not. Okay, so this was number 6, which is, again, very similar to number 13. Now we're going to look at number 7. Number 7, again, we're given a set of numbers, and we need to tell whether each operation is closed on that set of numbers. So for number 7, we have rational numbers. Rational numbers is our set. And we need to know, is addition closed on rational numbers? And that's going to be yes. If you take any two rational numbers and add them together, you will get another rational number, because you can take any two fractions and add them together by giving them a common denominator. And that is a rational number. Okay, part B, we have subtraction. And subtraction is always going to give you a rational number. If you start with a rational number, you will end up with a rational number. Multiplication, again, whoops, I didn't mean to start that. Multiplication is also always going to give you a rational number. Division will always give you a rational number. The only thing that will not give you a rational number is taking square roots. For if you're taking a square root, then the answer is no, because you could take the square root of 3, and that is not rational. So E was taking squares, which is closed on rational numbers.